Video is to talk about the properties that a solution will pick up when an acid or a base is dissolved in it. So a couple things to remember about acids and bases, especially when they're dissolved in water or other solutions. First is that pretty much all salts are strong electrolytes. And when we say salt here, we don't mean just sodium chloride, table salt. We mean that class of ionic compounds that is a metal bonded with a non-metal in an ionic bond. So sodium chloride is an example, but it's not the only one. And remember that salts result from an acid-base reaction. If we react an acid and a base, our products are water and a salt. And if we have a strong electrolyte, a salt, that will exist entirely as an ion in a solution. So remember, strong electrolytes by definition are things that completely dissociate in water. The sodium chloride in our example would completely break apart into sodium ions and chloride ions. And so when we're talking about the acid and base properties of salts, we're talking about the consequence of the reaction of their ions in a solution. When we dissolve an acid in a solution, it breaks apart into its ions, and those ions being dissolved in the solution give the solution its properties. Now there's a very special specific class of these reactions called hydrolysis reactions, and these are situations in which the ions produce hydrogen or hydroxide ions in water. So a situation in which the ions act as acids or bases in water to produce these ions. So when we talk about hydrolysis, there's four possibilities. We could have dissolved a strong acid and a strong base, in which case we will produce a neutral salt. Strong plus strong, we get a neutral salt. We could have combined a strong acid and a weak base, in which case we will produce an acidic salt. The acid here was stronger, the resulting salt is a bit acidic. If we have a weak acid and a strong base, we'll have a basic salt. If both are weak, both the acid and the base are weak, then our salt is going to depend on which has the greater dissociation constant. Those are our four possibilities. So when we think about the salts splitting up in water, we're going to have an anion and a cation floating around, one positive and one negative. So we'll look at the anions first. The resulting anion would be the conjugate base of an acid. So any general acid, that's H bonded with another element. If the H is donated, the leftover anion is our conjugate base. So if this anion comes from a strong acid, then it's neutral. Remember from our previous lessons, the stronger the acid is, the weaker the conjugate base is. So if we had an anion from a strong acid, then once it is split apart, once it is floating around in solution as just its ion form, it's considered neutral. If the anion comes from a weak acid, then as a conjugate base, it is basic. It will go on to react with the water, such as this reaction down here. We've got a conjugate base here, the leftover anion from a weak acid, and it can react with the water to pull one of the hydrogens away and leave hydroxide ions. So that's an important one. If we put a weak acid in solution, the conjugate base is going to go on to react with the water to make hydroxide. And we could calculate the pH of this solution using equilibrium principles, just like before. So the big takeaway from this slide to remember is that the anions that came from strong acids are neutral. Anions from weak acids are basic. Keep that in mind for our example problem later. Now it's time to talk about the cations. There's a little bit more to cations. They've got a bit more options. So a cation with an acidic proton would lower the pH of a solution. So NH4, for example. Our cation here is NH3, and it has picked up an extra proton, an extra hydrogen ion. So it's a cation NH3 plus an acidic proton, and this will lower the pH of a solution. It will make it more acidic. Most metal cations that are hydrated in solution also lower the pH. So most metal cations that are attached to a hydrogen will make the solution more acidic. This is because there's an attraction between non-bonding electrons on the oxygen in the water molecule and on the metal ion. And so we get a shift in the electron density on these water molecules. As a result, the OH bond here in the water molecule becomes more polar, and so the water becomes more acidic. So the more charge that our metal ion has, the greater it will be able to pull on those electron pairs on oxygen, and so the more polar it's able to make water, the more acidic. And the smaller the size that the cation has, the stronger it's able to pull. Remember, small size means that there is still a pretty strong force here at the outer boundary of this atom from the inner protons in the nucleus. Here, in contrast, we've got a bigger atom. It's more spread out, and so the nucleus here in the center, where all the protons are, is not as strong when we get all the way out here. So the effect is greater for cations that are very small, very consolidated, and have a higher charge because the charge is more effective at that outer boundary. So our general rules here, cations tend to make the water more acidic, and this effect is greater for cations with a larger charge and smaller size. Here's a couple other rules. So again, metal ions, or cations, tend to be positively charged, and so they will attract the water molecules because of the lone pairs on the oxygen. The higher the charge is, the smaller the metal ion is, and the stronger this pull can be. So to give you one example, any hydrated metal ions will act as acids. So iron, for example, can react with water and give up a hydrogen, meaning it fits the definition of acids here. Here we had a hydrated iron ion, and that's able to give up one proton, one hydrogen ion to the solution, giving us an acidic solution. The pH will decrease, so the solution will become more acidic as the size of the ion decreases, so for smaller ions, and as the charge on that ion increases. So between calcium and zinc, for example, the smaller ion is going to have a greater effect on the pH. It's going to be more acidic. And between sodium and calcium, the greater charge is going to have a greater effect on the acidity. Same for zinc and aluminum. greater charge, greater effect. It'll decrease the pH more. It will make the solution more acidic. So typically, we have a combined effect. Typically, we've got cations and anions in solution. So to summarize the rules here that we need to keep in mind, an anion from a strong acid will have no acidity, no basicity. It will have no effect on the pH of our solution because it was the conjugate base of a strong acid. It's negligible. An anion that is the conjugate base of a weak acid will increase the pH, so it will have a base effect. A cation that is the conjugate acid of a weak base will be acidic. It will cause a decrease in the pH. And finally, metal ions will typically cause a decrease in pH, with the exception of the alkali metals and the alkaline earth metals. When a solution contains both cations and anions from weak acids and bases, we will need the dissociation constants to determine which is having a greater effect on the pH. Whichever is dissociating more is going to be more present, and so it's going to be able to have a greater effect on the pH. In this case, we would turn to our ice tables to calculate pOH and pH, just like we did for weak acids and weak bases. We're doing the same thing, just now with ions instead of full acids and bases. Alright, this is really just restating those rules once more to talk about them before we look at an example. So a couple things to check. Look at your anion. Ask yourself if it is the conjugate base of a strong acid or a weak acid. If it's the conjugate base of a strong acid, it has no effect on the pH. If it's the conjugate base of a weak acid, it will increase the pH. It will make the solution more basic. Then we would turn and look at our cation. If the cation is the conjugate acid of a weak base, it will decrease the pH. It will make the pH more acidic. Here are a couple of examples of different salts dissolved in solution and their pH. We're going to do some example problems in just one moment. Alright, the other half of these, if the cation is from a strong Arrhenius base, it will not affect the pH. So just like the anions, if the cation came from a strong base, it has no effect. It is weak. Other metal ions will cause a decrease in pH. So other metal ions will be acidic. And again, if we've got both, if both the anion and the cation are going to have an effect, because they are both the conjugate bases, or they're both the conjugate pairs of weak acids and bases, the effect is going to depend on their dissociation constant values. So here are some examples. We want to know whether each of these salts, when dissolved in a solution, is going to be acidic, basic, or neutral. So take a minute to think about these yourself. Maybe have the slides next to you so you can go back and look at those rules. And then we'll talk through each of these examples here momentarily. Alright, so to talk through the first one, if we're looking at this first salt example, we've got sodium, and so that's going to be our cation. So what we're doing is we're going to look at our strong bases and consider whether sodium is the conjugate acid of any of our strong bases. And like I said, you will eventually want to be familiar with these so that you can have these memorized, since you won't always have a reference table. But I've included it for now. So we see that sodium does appear in the strong bases. So it's, as a conjugate acid, it's going to have no effect, right? Sodium, the sodium ion would be the conjugate acid of a strong base, and as a result would have negligible acidity. So the sodium is having no effect here. Our anion is ClO. We see that that does not appear in our strong acids. It is in fact the conjugate base of a weak acid. And so the conjugate base of a weak acid is basic. So this solution as a whole will be a basic solution. The sodium had no effect. The ClO was a basic anion, and so overall our solution is basic. And the other examples, you should be able to follow similar logic through. Here are the rest of the answers for these. You've got a couple problems on your homework that use these principles, so make sure you're able to follow the logic through these as well. So here we've got iron as our cation. It does not appear in our strong bases, so it is the conjugate acid of a weak base, or it is a metal ion. Either way, both of those conditions would mean that it has an acidic effect. It's going to decrease pH because it's a metal ion. And we see NO3 here is the conjugate base of a strong acid, so it will have no effect. So overall, we've got acidic, no effect. Our overall solution is acidic. Potassium, the conjugate base, or the conjugate acid of a strong base, it will have no effect. Bromine, as the conjugate base of a strong acid, will have no effect, and so our solution is neutral. Lithium, as the conjugate acid of a strong base, is neutral. ClO4, as the conjugate base of a strong acid, is neutral. Our solution is neutral. Sodium, again, the conjugate acid of a strong base is neutral. HCO3 is the conjugate base of a weak acid. It doesn't appear here. It is basic. Calcium chloride, calcium is neutral. It's the conjugate acid of a strong base. Cl2. Chlorine is the conjugate base of a strong acid. It is neutral. NH4, NO3. NH4 is the conjugate base, or the conjugate acid, of NH3, ammonia, a weak base. So it is acidic. NO3 is the conjugate base of a strong acid. It is neutral. We've got acidic and neutral, an overall acidic solution. And finally, nickel is a metal ion. It will be acidic. Iodine is the conjugate base of a strong acid. It is neutral. So we have an acidic solution. Alright, like I said, try applying that same logic and thought to the homework problems that ask whether a solution will be acidic, basic, or neutral.